Hey guys, I made this video for those that went through all the other videos and their understanding is decent but not fully harnessed. And this video we're going to go through the entire beam design process a little quicker. So not for someone who's a true beginner, but not someone who fully grasps it either. It has a little bit of understanding to still grab. So when we begin the beam design process, we are already assuming that you know how the beam is loaded and the length of the beam. If you know how the beam is loaded and you know the length of the beam, you can determine the max moment and the max shear. That's on you to get when you are ready to begin this step. So once you have the max moment and the max shear, you are ready for this step. The first thing you do is you take the max moment from either the diagram or the equation and you multiply it by 1.67. Once you have that multiplied by 1.67, you divide it by your yield stress, which is based on the material that's going to be given to you. And that gives you your plastic section modulus. The plastic section modulus is what we are going to take when we go to that website. So that website is going to tell us the plastic section modulus for each beam that we have, or each beam that we could choose from. And we will always choose the member that has, or the lightest member, I should say, the lightest member that has a plastic section modulus Z of X that is greater than what we just calculated from the previous slide. And the plastic section modulus is based solely on the geometry of the I-beam. It has nothing to do with the material. That's why we took out the material when we divided by the yield stress in the previous slide. So once we know what our Z of X is, say it was 17, you choose the lightest member that could support 17, which would be a W10 by 17 in this case. Once you do that, we can kind of go through this one again. I think you should know what this means. Actually, I'll pause here for a second. Remember that it's the second number, which tells you the lightest or the weight of it. The first number is roughly the depth. And the second number is the pounds per foot. So for each 1 foot of beam of this size, how many pounds is it? So the weight of the beam determines how much metal is used, which is how much it costs. So the lightest and cheapest beam will have a smaller number for the second one. Okay, so this slide right here is a very good summary if you want it all on one hub. Find max moment, multiply by 1.67, divide by f of y, find the z of x at least that much, and then we had checked moment. Now we're going to use that beam we chose to check shear and deflection. Remember, beams will almost always fail from moment. That's why we don't do shear first, because it wouldn't really help us too much. We're going to keep redesigning it. We check for the smallest size that we need for moment, and then we check shear. Then we'll check deflection, which often makes us need to redesign, but it's not that bad at that point. So now we have the beam, we're going to go to shear. So the actual shear that we're going to be applying to this beam is the max shear multiplied by our factor of safety, which is going to be 1.5 this time. So we take our max moment, max shear multiplied by 1.5, and we put that number off to the side. Then we check what our shear strength is based on the beam that we chose in the last step. So the formula for that is 0.6 multiplied by the yield stress multiplied by the area of the web. How do I know what the area of the web is? Well, I gotta go to the website and figure out what the area of this highlighted region is. The height of this is D. The width of this is the thickness of the web. I get that from the chart. This is a W, well, any random one. You choose it, look at the depth, the thickness, multiply together, that's your area of the web. So area of web times f of y times 0.6 gives you your shear strength. Just be mindful that you always want to be in the same units, whatever this is. This is going to be typically kips, so then for f of y you would use KSI. Okay, you got to make sure that this value is higher than what you got over here, and if it is, we're golden. It almost always will be, but you got to check it anyway. Once we do that, we're ready to check deflection. So here's your steps again if you want to read through that. And then we're going to move on to deflection. So first, you got to figure out what deflection you are allowed. The allowable deflection. And that's going to be the length measured in inches divided by 240 for dead and live loads, and then L divided by 360 for just the live load portion. And the actual deflection is going to be based on the way the beam is loaded. So I will always give you beams that are loaded in a way that you're able to use the shortcut formulas. And one of the shortcut formulas that you'll see is for deflection over here. So then you'll do, in this case, PL cubed over 48 EI. P is the point load right here. You got to be mindful that P will sometimes be dead and live applied to the same part. So when you're doing divided by 240, you do the dead plus live. When you're doing just the live load portion, the L over 360, you're only going to be doing the P that constitutes the live load portion. L is the length of the beam. Make sure you are measured in inches. You probably have to multiply it by 12. E is the modulus of elasticity. We'll pretty much always be using steel, so it's going to be 29 million psi. We're going to use pounds per square inch, not kips per square inch, because I right here, which is inertia, is going to be measured in inches to the fourth. And you get the inertia by going to the website and looking at the inertia on the x-axis for the beam that we have selected in step 1. You do the formula 2 times, and you will then compare what you actually have to what we're allowed. And if our actual is less than allowed, we're good. If the actual is greater than allowed, we're not good. And if it's not good, we will have to figure out what works. So you'll have to do that proportion like we did in the example. You'll take the actual deflection and you'll divide it by the allowable deflection. And that'll give you a number greater than 1, right? Because if it's not working, that means that the actual is a larger number than the allowable. So you do the actual divided by allowable, and then you multiply it by the original inertia of the original member. And that'll give you a larger inertia value. You take that larger inertia value, and then you go back to the website, and then you choose the lightest steel member that has a inertia equal to or greater than the inertia you just calculated. You can quickly check the plastic section modulus, but it's always going to be greater than what you did previously, right? Because it's going to be a larger value. Remember, inertia is the resistance to change, and it's based on the weight. So a heavier member is going to be stronger. So once you choose a new member based on the new inertia, you actually don't even have to check shear and moment again because you know for a fact that it'll work. And that is the steps. So then that video again was hopefully like a quick little 8-minute video to be able to just kind of go through the process for someone who just needed to fine tune a little bit of the process. We'll go through the example quickly too. Here's your beam right here, and I'll give you this whole thing. This is a great example that I'm going to be giving you. You'll know what W is, and you'll know that W is comprised of live and dead, and you'll know the span, and you'll know the material. So the first thing you have to do is get the max moment and max shear. You could do the diagrams. I would recommend using the equations. Once you get the max moment from the equations, multiply by 1.67, and then you get your design moment that we'll be using. Divide that by your plastic section modulus, divide that by your yield stress to give you the plastic section modulus, which is your 17.7 inches cubed. Note this step right here. A lot of students make a mistake right there. You got to make sure that you are in inches. Moment is always going to be in foot-pounds, but you want foot-inches, so you have to multiply it by 12. Don't forget that step. And then we get Z of X is 17.7. And then we go to our chart right here. And you find the lightest member that can handle 17.7 as our bending moment capacity. You might be tempted to say W10 by 17, but I'll tell you you're wrong, because the W12 by 16 is lighter because 16 is less than 17. And in fact, it's also stronger. So it's lighter and stronger. I'm going to choose that one. So now that we chose a W12 by 16, we're going to check the shear. The shear, we take the max shear from the formula, multiply by 1.5, and that gives you your shear that's actually applied. And then we need to check what the shear strength is, which is the 0.6 F of Y AAW. AW is the area of the web. You get that from the chart, which tells you your depth, multiplying by your thickness of the web. So I see 11.99 for the depth, 0.220 for the thickness of the web. So I multiply 0.6 times F of Y, which is 50,000 PSI, times 11.99 times 0.22, plug and chug, gives us a shear of 79,134 pounds. That's how much shear this beam could actually handle, which is way more than what we are applying. Again, it will rarely fail from shear. Then we check the deflection. So we take our length, make sure you're in inches, don't forget it, divide by 240 to give you your deflection allowed from the entire dead plus live, as well as the deflection allowed from just the live portion. Our max deflection from the design load is given by the beam shortcut formulas, and because we have a simply supported beam with a distributed load, the deflection is the 5WL to the fourth divided by 384 EI formula. So W is the overall pounds per foot applied, and we'll do the dead and live first, so it'll be the two numbers added together, which gives us 1,090. However, that's pounds per foot, right? But we want to always be in inches. So I'm going to divide this by 12 to get pounds per inches. Then I'm going to multiply it by the beam length, which is measured in feet. So I have to convert that to inches as well. No, you can't say they cancel out because we have it raised to the fourth power here. So 1,090 pounds per foot divided by 12, multiplied by 18 times 12, that quantity to the fourth power, divided by 384, then the E for steel, which is 29 million pounds per inches squared, multiplied by the inertia in the x direction, which from the chart reads 103. Notice what cancels, and then you are left with an inch value, and we get that the actual deflection is 0.86. We were allowed 0.9. We are good. We then have to check the live load deflection. Similar thing. The only thing that's going to be different is the W will be just from the live load, and we're going to be comparing it to the L over 360. And we find that it does not work. So what do? You cry. After you're done crying, you do the same thing again with a larger beam. However, you don't start from the top. You should be able to realize that the only thing that's changing from the deflection formula from one beam to the next is the inertia. So I can figure out what inertia I need to give me a deflection that's suitable. So you do that by setting up a proportion. You take the actual deflection divided by the allowed deflection, and you multiply it by the original inertia. Because actual over allowed will be greater than 1, you're going to be increasing the original inertia to give you an inertia that will work. So I know that I actually need an inertia, or a beam that will give me an inertia of 108.15 or greater, which will give me W12 by 19 as my next lightest member with an inertia that works. And because the plastic section modulus and the depth and the thickness of the web are all greater of a 12 by 19 as compared to a 12 by 16, I don't even have to check moment and shear. I know it'll work. And then that will be my final answer. A 12 by 19 beam is the exact beam that an engineer would order for this member.